Good day, everyone. My name is Juling Shih from National Central University, Taiwan. It's my best honor to introduce Professor Mu-Chun Chen, who is the speaker of today. She's a theoretical particle physicist at the University of California, Irvine, researching the properties of the elementary particles and fundamental forces of nature. She's also the Associate Dean of Diversity, Equity, and Inclusion of the School of Physical Sciences and was the Vice Chair of Graduate Studies. Her research area is theoretical high-energy physics, focusing on the origin of neutrino masses and oscillation. Among many awards she has won, just to name a few. In recent years, she was UC Irvine's Dr. Dick Gallo Professor of the Year Award nominee, and she has won Department of Physics and Astronomy Undergraduate Teaching Award and School of Physical Sciences Outstanding Contribution to Undergraduate Education. Having this said, we shall not waste more time listen to me, but to hear from her directly. Without further ado, let's welcome Professor Chen to give her talk on neutrinos, a window into physics at the early universe. Professor Chen?
All right, so Shih, thank you very much for this kind invitation. Can you hear me well? Yes. All right, so
yes.
Let me share my slides here. Give me just a second. Are you able to see my slides?
Yes, it's coming up. Yes, we can see that.
All right, very good. 所以非常谢谢施教授的介绍。然后今天是非常荣幸有这个机会跟大家分享一些我的研究。So as Professor Shih was mentioning, my research is in the area of theoretical elementary particle physics. And this concerns phenomena at a scale which is very different from the scales that are relevant to the phenomena, the science that we have heard in the last 4 lectures. So last month, we had this excellent lecture by Professor Zhongpei Ma on macroscopic black holes. This, of course, concerns scale that is very, very large, the astronomical scale. Where in the discussion, biomedical imaging, semiconductor engineering, and nanotechnology, this concerns science that are at a scale which is about 10 orders of magnitude smaller compared to the size of a human being. So elementary particle physics, this concerns actually very, very, very tiny scale. It's almost more than 30 orders of magnitude compared to the size of the human being. And the goal here, by studying the properties of the elementary particles, our goal is to be able to understand all the physical phenomena at the most fundamental level. And of course, the quest to understand what is the world made out of and what hold it all together, this is nothing new, but it started already in the very, very ancient time. So in ancient Western philosophy, there was already the notion that the 4 classic elements, 基本元素, which include the air, 火, earth, 2, water, 水, and fire, 火, are the 基本元素 that is that is accounting for all the physical phenomena. And of course, equivalently, in our Eastern philosophy, we have the 金木水土火 as the 5 elementary, the 5 classic elements. So of course, today we know there are actually something even more fundamental than 金木水土火, right? So in fact, you and I and all our everyday objects are made out of 3 kinds of tiny particles. And these are the electrons, 电子, the protons, 质子, and the neutrons, the 中子, where the protons and neutrons, they bind together to form the nucleus, and the electrons are orbiting around the nucleus. And this, of course, together, they bundle up to make atoms, 原子. And atoms are the building blocks of all of us, you and me, and the buildings we are in, and all the planets. But the question is the entire universe made out of just electrons, protons, and neutrons, right? So the answer is no. Actually, for any one of the electrons or protons or neutrons that are in the universe contains 1 billion neutrinos, all right? So neutrinos turns out to be one of the most abundant particles in the universe. And as a result, in order to understand the universe, we need to understand the neutrinos. So just to give you some idea, some perspective of how many neutrinos there are. It turns out there are 10 million neutrinos from the Big Bang, left over from the Big Bang, within each cubic foot of space. So if you take a regular person, a small size like me, in the volume of me, there are about 30 million Big Bang neutrinos. So there's a lot of them. One of the sources of neutrinos is the sun, right? So 太阳制造很多很多中微子. And it turns out there are 100 trillion, 100万亿 neutrinos coming from the sun, passing through each of us at every second. Okay? And the reason for this is because the sun shines due to the fusion reactions inside the core of the sun. And through these fusion reactions, 核能反应, it also produces both the energy, which include the visible light, and that's why the sun is shining and warm us, right? There's the energy from the sun. Through this interaction, it also produces the neutrinos, 中微子. In addition, the sunshine and it produces atoms which are more complicated than the hydrogen atom. Right. So you may wonder, we have so many neutrinos passing through us. Do we have to worry about, being harmed by the neutrinos? The answer is no. And the reason is that because neutrinos, they interact with matters very feebly. So to neutrinos, we are just like empty space, and they're just passing through us without interacting. So typically, one solar neutrino would have to go through, 10 to the 19 people before it can do anything. So you can use this number and turn it around and ask what is the probability of a solar neutrino interacting with one of us. And this probability 几率 is very, very low. So this is 1 in part of 10 to the 19, right? So given this feebleness, it also makes neutrinos very hard to detect. 所以实验上非常的困难，因为中微子它没有什么交互作用，它的交互作用非常非常的弱。All right. So if there were no neutrinos, then the sun and the stars will not shine. And therefore, there won't be energy from the sun to keep us warm. And there were then no atoms which are more complicated than the hydrogen atoms that can be formed. Right? If there were no neutrinos, then there would be no supernova explosions, where we depend on a small amount of heavy chemical elements like the zinc and selenium. And these elements can only be produced in supernova explosions. And therefore, this shows you neutrinos are actually very important to our lives. All right, so we already seen the structure of the atom, which contains the nucleus with electrons surrounding around the nucleus. You may wonder whether this is the most elementary constituents of nature. And it turns out it's no. In fact, the nucleus are made out of the protons and neutrons. Where protons and neutrons, again, are not the most fundamental constituents, but rather the protons and neutrons, they are made out of quarks. So here in this plot, you can see this relative scale for the atom. This is about the scale is about 10 to the minus 8 centimeters, where the nucleus has a size which is 4 orders of magnitude smaller. If you keep zooming in, the nucleus is of the size of 10 to the minus 13. And so this is basically the smallest scale smallest constituents that we know of. And you may wonder whether we can further break the quarks apart and see the constituents of the quarks. And so far, we still don't know the answer to that question. All right, so now I've introduced the smallest, the fundamental constituents that made out of matter. Another thing that I need to tell you is what are the forces that hold all these fundamental constituents together to make matters, right? It turns out there are 4 fundamental forces. 2 of them are very familiar to you, to us. The first one, which is we experience it in our everyday life, is the gravitational force, 地心引力, right? So this is a force that is responsible for explaining why the sun is orbiting, why the Earth is orbiting around the sun. And this is also the force that explains why the apple fell down from the tree. Another force which is familiar to us is the electromagnetic force, the 电磁力. So this, of course, is relevant for explaining phenomena such as the lightning, 闪电, and it also explains why there's the attraction between the magnet, 磁铁, and the nails, right, the metal. So in our everyday life, we only observe the gravitational force and the electromagnetic force. But there are 2 more fundamental forces, even though we don't see them with our eyes, but they exist. And these are the so-called strong force, 强力, and weak force, 弱力. And together, these are responsible for the interactions among the elementary particles. Right. And given that, even though gravity, we experience it everywhere, gravity is everywhere, gravity turns out to be the weakest of the 4 fundamental forces. All right. So we heard about, neutrinos being produced due to the fusion reaction inside the sun. And in fact, the weak force is that force that's responsible for the fusion reaction, which of course is inside the sun, but it is also the type of interactions that explain what takes place in the nuclear power reactor. Where the strong force is a force that binds the protons and neutrons together so that they form a stable nucleus. All right. So the tool that particle physicists use to study the properties of the elementary particles, there are, of course, many such tools. And one of them, which you may be familiar with, is the colliders. So right now, the highest energy machine that we have is the so-called Large Hadron Collider, 大型强子对撞机, which is located at a lab called CERN, which is located near the border of Switzerland and France. So this is a facility which is really big. And from this picture here, what you show is, the path of the proton beams, and the circumference of the path is 27 kilometers long. So it's like huge. And there are two proton beams which travel at very, very high speed, and they collide. So how fast do they travel? They travel at a speed which is close to 300,000 kilometers per second, right? And once they collide, they produce, because of this high speed, there are a large number of collisions that is being produced. And so it's roughly 10,000 collisions per second that are being produced. And these are very, these are like really large facility. So just give you some perspective. On the right, you see a picture. This is a so-called Atlas detector, where you can see that the size of the human is very, very tiny compared to the size of the detector. All right. So the maximum energy of this collider is 14 TeV. So the TeV is sort of the unit that particle physicists use. And you may wonder, how big is this energy? This turns out is, it's just a kinetic energy of a mosquito, right? So this seems to be very small, but is that really it? So a mosquito contains about 1 to 10 moles of atoms. So I'm just doing a back of envelope calculation. So this is roughly 10 to the 23 to 24 atoms. Where each atom has one or more protons, right? So there's an order one number of protons. So even though this total energy is roughly the kinetic of the one mosquito, but now at the Large Hadron Collider, this energy is packed into just one single proton. So this is actually a really, really large energy, right? So with this energy, we can break the protons apart and study its constituents, all right? And this is a way that particle physicists go ahead and discover all the elementary particles and study their properties. All right, so this is our current knowledge of the the entire set of matter particles. We have 6 quarks, quark, and 6 leptons. I think that the translation is 亲子. So for quarks, we have something called the up quark, down quark, chum quark, strange quark, top quark, and bottom quark. Where for the leptons, you are familiar with the electron. There's something also called the muon and tau. And there are 3 additional leptons, which are the electron neutrinos, muon neutrino, and tau neutrino. So I put all the 6 quarks and 6 leptons in a very peculiar way. This actually, there's a reason for that. Because if you look at just the property, the charges, electric charge of the particles, family 1, family 2, family 3 particles, they all look the same. But their masses are very different. So we will come back to this aspect later. And another thing that you discover is that we have in the first family, I have the electron, and there is something called the electron neutrino. So that gives you some sense that these 2 leptons are actually connected. Likewise, muon has its partner called the muon neutrino, and tau has its partner called tau neutrino. And again, we'll come back to these properties later. All right, so in addition to these 6 quarks and 6 leptons, we also have the force carriers that mediate, that transmit the 4 fundamental forces, right? So we've seen the 4 fundamental forces: the gravity, the weak force, the electromagnetic force, and the strong force, where their corresponding force carriers are the so-called graviton, which has not been observed yet. But for the weak electromagnetic and strong force, their force carriers have been discovered. And these are the W and Z bosons, which mediate the weak force that fuel the fusion reaction. The electromagnetic force has its force carrier, which are photons, the 光子. And for the strong force, the force carrier are called the gluons, 胶子, I think. Okay. And in addition, we have the so-called Higgs boson, which you might have heard of, in the news in recent years. And this was actually the very last particle within the standard model that was discovered. And these particles, sometimes it is called the God particle, 上帝粒子, you may have heard of, because this is a particle that is responsible for giving masses to all the elementary particles. So what I show here is an actual event at the CMS experiment at the LHC, and I believe Taiwan has very big presence at CMS. And this is an actual event of the Higgs particle discovery. So you have two beams coming in, they collide, and protons get broken up and produce subsequent particles, which then subsequently turn into other particles. And just by studying these very complicated interactions, we are able to deduce the properties of this elementary particles, and possibly discover new particles that we haven't thought about. All right, so just to sum up, we have the strong force, weak force, electromagnetic force, and gravitational forces. These four fundamental forces, together with the fundamental elementary particles that we saw, together they govern the evolution of the universe from the Big Bang into today's observed universe. And all this, this knowledge is together. This is called the standard model of particle physics, 标准模型. And without these four fundamental forces and elementary particles, you and I cannot exist, right? So this is important. But you may wonder, now that the Higgs particle is discovered, is a standard model then the theory of everything, right? Whether it can really explain all the phenomena. And the answer is no. And this comes to the neutrinos, right? So as we saw earlier in this, table, the particle zoo, we've seen that neutrinos come in three flavors. So think about this as, the ice cream, right? We have the strawberry flavor, the chocolate flavor, and the vanilla flavor. And for neutrinos, that's the same. We have the electron neutrino, muon neutrino, and tau neutrino. It was thought for many decades that neutrinos do not have mass, right? 它们没有质量. That was a previous prediction. But after many decades of searches, it was confirmed and discovered that neutrinos, they oscillate, and therefore neutrinos have masses. And this led to the Nobel Prize in Physics in 2015 to Professor Takaaki Kajita-san from Super Kamiokande collaboration. And I saw that Kajita-san will be giving a talk in December in Taiwan. So this is actually exciting. And sharing the prize together was Professor Art McDonald from Sudbury Neutrino Observatory collaboration. Right, so Nobel Prize in Physics 2015, it was jointly awarded to Kajita-san and Professor McDonald for the discovery of neutrino oscillations, which indicates that neutrinos have mass. All right, so here just to give you a sense of what type of experiments that discover the neutrino oscillation. And this is an example, this is a picture of the Super Kamiokande experiments, which produce the neutrinos at the KEK. So this is a 大型加速器 in Japan. And the neutrinos then travel a long distance, several hundred of kilometers, and reach the detector located at the Shengang 粒子研究 facility in Kamiokande. And this detector is a water Cherenkov detector. So this is a big detector which is filled of water, as you can see. And all these little balls are the so-called PMT photo multiplier tubes. And so making use of this detector, one can detect neutrinos and study their properties. And again, just to give you some sense of the scale of the experiment, you can see there are 3 staff members sitting on a boat. And the boat is, on top of the water, and they were like fixing the PMT tube. All right. So this phenomena of neutrino oscillation, this is it turns out to be quantum mechanics at work at a macroscopic scale. So the way it works is at the neutrino source. Let's see whether I can slow this down. At the neutrino source, only one flavor of neutrino get produced, right? So let's say this is a Mu-Chun neutrino, or say neutrino of the strawberry flavor, right? So it's all red. So this is a neutrino source, 中微子 the 来源 the source. And now this neutrinos travels toward the detector over some, some long distance, right? It could be several hundred of kilometers or even thousands of kilometers. Through their propagation, they actually turn into other types of neutrinos. So here, just give you this example at the detector. 在碳微器这边, what you discover is there's no longer 100% of red neutrinos, right? But you have some part of red and some part of blue. So what that is telling us is that, some neutrinos, of one type, one flavor, turn into neutrinos of a different flavors, right? So this whole thing is, this phenomena is called neutrino oscillation. All right. So, with some quantum mechanics, you can show that neutrino oscillation require neutrinos to have masses. And the way to understand this is that through the propagation, even though neutrinos were produced of one type, right? It could be electron, muon, or tau neutrinos. But when they propagate, actually, they don't propagate, each of these flavors do not propagate as a simple harmonic oscillator, but it is the mass eigenstates that propagate as a simple harmonic oscillator through the Schrodinger's equation. So in other words, the neutrino of each flavors are made out of neutrino of 3 different mass eigenstates, or maybe let me turn it around. Neutrino of what we call electron neutrino, muon neutrino, and tau neutrinos, they turns out not to have definite masses. But neutrino states that have definite masses are the nu1, nu2, nu3. So you have some composition of nu1, nu2, nu3 that make up of nu e, nu mu, nu tau, right? So through the propagation, nu1 propagate as a simple harmonic oscillator. Nu2 propagate as a simple harmonic oscillator. So the amplitude does not change, the wavelength does not change, and likewise for nu3. But given that nu1, nu2, nu3 are superposition of nu e, nu mu, nu tau, now you have this oscillation phenomena. In other words, You could start out with neutrino of one flavor, which has some part of nu e, nu mu, nu tau. Each of them would oscillate as a simple harmonic oscillator, but each of them, nu1, nu2, nu3, do not have the same wavelength. At the detector, you may get a different composition, right? And that's how you get, different flavors, compositions at the detector. All right, so I hope this is not too confusing. But the bottom line is, the standard model predicts massless neutrinos. And now, and in order for neutrinos to oscillate, as I told you earlier, neutrinos must have masses. And therefore, by discovering neutrino oscillation would indicate that neutrinos have mass, and therefore that would indicate that the standard model is not enough. There must be new physics beyond the standard model, all right? And even though neutrino masses are non-zero, from the observation, we know that their masses are very tiny, right? All right, so you may wonder, what kind of new physics can give rise to, small enough neutrino masses, right? The neutrino masses that are compatible with the observation. And it turns out neutrino mass generation actually is quite natural in so-called grand unified theory, 大统一场论, right? Through something called the Shih mechanism. So 中文翻译成 I think 跷跷板, right? Shih. So the idea is that in grand unified theory, there is a new particle called the right-handed neutrino that is being predicted. And given that the right-handed neutrino is very heavy, this somehow through the Shih that give rise to a very small neutrino mass that we observe. All right. So again, the quest for having a grand unified theory, this is also a long quest, but we do have a lot of evidence along the way. So first of all, we know the gravity force actually is the single force that account for phenomena that are at two very different scales, right? It explains the celestial motion, which is at the astronomical scale. It also explains the terrestrial motion, like the apple fall down, right? So this is a smaller scale. But even though the scales are so different, these two phenomena are explained by gravity force. Likewise, the electric force and magnetic force, we know, due to thanks to James Maxwell, these are unified into something called the, these are just two different aspects of what we call the electromagnetic force. Einstein actually has attempted or has tried, but unfortunately did not succeed to find a grand unified theory. But this is something that he was trying to do, the ultimate quest that he had, during later part of his, research career. So the idea here, perhaps there is a super force that can unify all these four fundamental forces. So instead of four individual forces, perhaps there's just one single force that can explain all the four forces and phenomena associated with these four forces. So we've come a long way since Einstein's quest, and right now, we have the understanding that the electromagnetism and the weak force, these are just two different aspects of what we call the electroweak model. And we also know, both theoretically and experimentally, to some extent, that electroweak force and the strong force can be unified into something called the grand unified theory, grand unification. So, however, we still don't know how to unify the gravity with the other three fundamental forces. And perhaps this may require, string theory or, quantum gravity, or, we still don't know yet. All right. So here, just to give you, a proof that, we do have evidence, suggestions, there could be a grand unified theory. So I hope this plot doesn't scare you away, but I will walk you through it. So what I plot these three curves, they basically are the strength of the three fundamental interactions. So you have the electromagnetic interactions, which is the top line. You have the weak interaction and the strong interaction. Where on the x-axis, this is the energy scale, or you can think about it as the length scale. Like, so when I go to the right-hand side, this is higher in energy, but lower, small, corresponding to smaller length scale, or further back in time in the evolution of the universe. And what you notice is that, miraculously, even though all the three fundamental interactions, they have very different strength at the low energy, which is on the left-hand side, right? You see that the strong force is much stronger compared to the electromagnetic force. However, once you get to the scale, which is roughly 10 to the 16 GeV, that's the energy unit we use, all the three interactions miraculously just meet at one point their strength, right? So this suggests that there could be a grand unified theory that go above, once this three interactions meet above the scale, there would be a grand unified theory. And it turns out the energy scale that is necessary for giving rise to neutrino masses that are compatible with the experimental observation turns out to be very close to this grand unified scale. All right, so in the remaining time, I'm just going to get down to this structure and ask a question about the origin of masses mixing and CP violation. And previously, I very quickly mentioned that the Higgs particle, this 上帝粒子, it is responsible for generating all fundamental fermion masses except for the neutrinos. But it doesn't really, this mechanism doesn't really explain why, all the particle masses are so different, right? And the tool I'm going to use is based on symmetries, so 对称性. And of course, this symmetries occur in many places in nature, right? We observe it both in the plants, in the flowers, also in living creatures like butterfly or starfish or a marmot. It also exists in the art or in our architecture. So what I've been working on in my research, a big part of my research, is to try to understand this pattern of the fermion masses making use of symmetry, right? So here, just to give you some perspective, if you put all the elementary fermion, the 6 quark, 6个 quark 跟6个亲子 all together, the size of each bar basically indicate, how heavy these particles are. So if I, rescale everything and make the top quark as 1, right? So that's my sort of the reference of the scale. Yes, top quark. Then you can see the bottom quark is 10 times smaller in its mass. The strange quark is 100 times smaller, etc. Right? So how do we understand? And for the neutrinos, this is even more, even smaller. So the question is, how do we understand this pattern making use of symmetry? Right. So the type of symmetries, one type of symmetries that I use is a grand unified theory, a symmetry that describes grand unified theory, which we saw earlier, the 大统一场论. Another symmetry, which you can think of it as, Fibb's force, because there's something that has never been discovered yet. And the symmetries are described mathematically through something called, group theory, 群论. So some of you might have heard of this or even studied it. And the type of symmetries that, they're having a lot, this is sort of a hot topics these days, is to use discrete symmetries. So for example, some familiar examples would be the symmetry of this perfect solid. And using the group theories that describe the symmetry of this perfect solids, the hope is we can have a fundamental understanding of this observed masses and possibly the mixing patterns that we have, both in the neutrino experiments and elsewhere, right? All right, so just a simple example of what is symmetry, and one example is this is a tetrahedron or 粽子, right? So it has a shape of a tetrahedron or 四面体. And this is a symmetry which has been utilized a lot, and I think this is something that may be fun for the students to do because you can really do it by hand, and I think everyone in this room will be able to do it. So this is the symmetry that describes the 四面体. This corresponds to even permutations or 偶数交换 of 4 objects, right? So you can actually work out how many different permutations you can have. And it turns out that there are 12 such permutations. So for example, if you start out with 1, 2, 3, 4, and you want to permute, say interchange, 就交换1跟2, that's like 1 permutation, right? And then you can interchange 1 and 3 again, then you lead to 2, 3, 1, 4. So this is 1 even permutation you can have. And here I give you another example. And of course, there is also geometrical interpretation of this symmetry, and that is a symmetry of the tetrahedron. So for example, For example, if you rotate this 粽子 by 120 degrees along this axis, of course, the 粽子, looks exactly the same, yes? Likewise, on the right, here I have a different rotation axis, and if you rotate 180 degrees, again, this 粽子 look exactly the same. Right, so this is a symmetry of the tetrahedron. And here I give you the perspective of both the geometrical interpretation as well as this more like algebraic, interpretation of what the symmetry is. It turns out with the symmetry, we can explain, using the symmetry to build models, and the model prediction can give rise to the observed this very observed masses for the elementary fermions, as well as the mixing patterns that we observe experimentally. And another very exciting prospect is that such symmetry may also help us to understand at a more fundamental level where does the charge parity symmetry violation come from? So this is 电荷 and mirror symmetry, 镜像对称的破学, yes. And of course, the CP violation, this is something very important in order to explain the matter-antimatter asymmetry of the universe. And so here, just to some of you may be familiar with a parity symmetry violation, 镜像对称破失 in the weak interaction, and this was actually theoretically a possibility that was proposed by Yang Zhening and Li Zhendao and discovered experimentally by Madame Wu Jianxiu. So it's actually pretty exciting. There's a lot of connection here. All right. So I think this is sort of hopefully to give you some flavor of what I do and the type of tools that I use. And of course, by understanding these properties of the neutrinos and also additional, other elementary fermions, we hope to be able to really gain an insight into what happened, within the fraction of a second after the Big Bang in the early universe. So, in the remaining few minutes, I just want to, just give you also some perspective of what I see, in this line of work, and where do we go from here? Just want to mention that it is very fulfilling to understand the universe, and this is a lot of hard work, and it's not always easy. But it's nice to be able to get to work with people from very diverse cultures. So it's a feel very international, and you get to travel a lot, so you get to see the world, and it's very rewarding to work with students from very different backgrounds. So for example, this is an example of the students that I currently or recently work with. As you can see, it's very diverse. We have international collaborations with collaborators both from Germany, also from Mexico, and our student bodies is also very, very diverse with many cultural and other their backgrounds. All right, so what can you do with a physics or more generally STEM degree? There's actually many things you can do. And I think that the important thing is if you would like to pursue, academic career, become a researcher, this is great and you should really do it. But even if, you are not so sure about going into STEM career, I think it is the type of training, right, in this process that is important. So with a STEM degree, a physics degree, you may go into, data science, security, education, policy, government policy, or patent lawyer. And of course, you may be an astronaut or, a researcher at national labs, engineer, or a professor. All right, and you can even be the head of state. It turns out the German Chancellor, Dr. Angela Merkel, she is a physicist. So just some words of encouragement. I think it's good to be ambitious, but be realistic. Prioritize things that are important to you. Be flexible and creative, and keep an open eye and open mind and embrace new opportunities. Be persistent, work hard, and follow your passion. All right, so I just want to link back to, just want to echo what our very first speaker, Professor Liu Kim mentioned. I think this knowledge is very, very important, right? You have all this good education, but I think the ultimate goal is make use of what you learn, what you study, what you learn, be kind to each other, and do something good for the whole human being, and enjoy the journey. So I will stop here, and I hope we still have some time for discussions.
Thank you, Professor Chen, for introducing us to our very close friend, neutrinos. Neutrinos, they are around us every day, but we have never met them in person. I think I know why Professor Chen won so many teaching awards since today, like today. She uses so many daily life examples to show us where our neutrino friends are and making them easier to understand. And I think from today on, I will start to look at mosquitoes differently. Now I'd like to open the floor for questions and discussions. And our audience, you can use the raise hand function on the Google Meet to ask questions, or you can leave your questions in text in the chat box in either Chinese or English. 你可以用中文问问题，我想陈教授应该是可以理解的。Before that, shall I initiate the discussion when our audience are preparing for questions? 我先用中文问，就是我看介绍，其实我今天前面没有介绍的一个是，好像陈教授讲，有这个叫发明吗？有产出一个新的方法，就是跟物质反物质不对称的一个方法，是不是叫做 Chen
Mahansapa.
Can you explain that to us
quickly? Yeah, so this is sort of what I alluded to in the later part of the slide, where in the discrete symmetry, 所以这个对称性discrete symmetries. There are certain symmetries that have very special property. They have something called the complex Cauchy-Gordon coefficient. So that doesn't make get too technical, but the point is that there are some new mathematics. The group has some properties that was not realized before, and with those type of symmetry, we are able to predict the amount of CP violation. So that's a pure, totally new origin that was not discovered before.
Wow. And that has
of course, with this, once you have this origin, you can then, what it means is you can predict how the particles and antiparticles behave differently.
Oh.
Right, so you have a more fundamental reason and even predict how they should be behaving.
Okay. That takes more expertise to understand it completely. That part I get. Okay. In the meantime, I think we have a couple audience asking questions in the chat box. If you want to look at the chat box in text, and I'd like to just repeat the questions for our other online audiences too. Okay. How do we estimate the total number of neutrino? Will there be new discovery of matter-particle quadrileptons in the future, and how difficult it is to find the new old one? Wow.
Right. So let's see. So let me answer the second question first. We don't know. So will there be new discovery of matter particles? Of course, now we know there are 3 families of quarks and leptons, right? So 6 quarks and 6 leptons. And there have been proposals that there might be 4th family. But the Large Hadron Collider has ruled out that possibility due to the Higgs discovery. So I can go into more details, but to have like exactly the same, the 4th family, that possibility is ruled out unless they are like super heavy, right? And super heavy meaning they are at a scale which is above the scale of the Large Hadron Collider, right? How difficult it is to find the new or old ones. So for the old ones, I interpret this is the one that already been discovered, right? So they can be reproduced in the colliders, and we can study their properties in more precision. Where to find the new ones, it really depends on how heavy those new particles are. And so again, this will tie to how high the energy the machine has, right? So the Large Hadron Collider has energy of 14 TeV, and our, the round 3 of LHC is, going to take place soon. And this, of course, can discover new particles, around the TeV regime. But if you have something which is 100 TeV, then, with a Large Hadron Collider, there's no hope, right? Because you don't get enough energy to produce those new particles, right? So this is sort of, one direct approach. You just break up the protons and try to produce those new particles, and that would require very high energy. However, there are like indirect methods, such as rare processes like neutrino oscillation, or there are some other processes which I didn't cover in this talk. And so, for example, if you have the forced neutrino, it would change how neutrino oscillate, right? So it would change the probability of what. How should I say this to make it clear? It would change the theory prediction, right? So, neutrino oscillation would be one way to discover such zero neutrino. So this is a new lepton, right? So there are other processes which do not occur very often, meaning because of the interaction strength is very weak. But those rare processes are actually very important as a complementary method approach to the collider experiment in order to search, new particles if they are very heavy. And the first part of the question, how do we estimate the total number of neutrinos? So this is, we rely on there's a cosmological and astronomical data. So that's again a very complicated story. But you do really need to take different pieces of the data together and try to get a coherent picture and get a number. And I should mention that this is just the estimate, because we have no idea. We don't have a complete picture yet. What happened, what happened right after the Big Bang. So if there are new physics at a very, very high energy scale, meaning near the grand unification scale or above, they may change the estimate, right? So again, it is your estimate, and there are new physics scenarios that may change our current knowledge, our standard notion of the number of neutrinos we expect. All right, so I hope that answered the question.
Okay, thank you.
So it's a very abstract.
Yes, thank you. But now we go to a less abstract question. Our professor asked, can you tell how much mathematics the students would have to learn to do theoretical physics?
Right, so this is a good question. Again, theoretical physics, there are different approach to do theoretical physics. I'm consider myself a model builder, right? I use all these tools, the symmetry. There are other tools at hand, and with that, I can write down a new model and then make predictions. So the type of math that I use very often, most frequently, is group theory, like 群论, because this is really the language of particle physics. Like, yeah. And of course, I mean, theoretical physics, there's also, more sort of phenomenological end, right? So it's closer to the experiment. And therefore, the type of math they use would not be as sort of, the amount of math will not be so heavy, right? But I would say group theory is very important. But usually I get questions from students whether I need to go to the math department and take a mathematics course. And it really depends, right? So I think it is good to have those background, but also keep in mind, mathematicians, they have very different focus compared to theoretical physicists. So mathematicians, they care more about the derivation, right? Whether it's logical derivation, where physicists, we just make use of the result, right? So the focus is very different. But having very strong math background, that's important. And another thing I want to add is a lot of time, you really learn the math through the research. So Professor Shih, you mentioned about this CP violation, the Chen-Mahansapa mechanism. And that was a totally brand new time that, particle physicists didn't really had not thought about discrete symmetry that much at the time. So we really need to go and really learn the math in the process. And through the learning, we discovered those new properties, and that's how we lead to our sort of proposal discovery, right? So I would say, it's both, right? You need to have a very good background in math, but it doesn't mean that you have to learn everything before you can embark on the research. Right, you also learn through that research process. So I hope that answered the question.
Yes. Then can you also tell us a little bit about how you get into this field? How you started this?
Very, very, very nice. So I actually had a few slides which I didn't show. So about my journey. 我在高雄出生，然后在屏东长大到4年级。And then 我家人搬到台中 so I basically spend most of my time in 台中 and so when I was in 在小学的时候很想当数学家but then 到国中的时候我接触到物理课 so I mean that sort of just draw my attention because physics I feel 我有比较多的 intuition as compared to math不过在同一个时候I mean it's a struggle because I also love music I play the piano very intensely so it's sort of have to decide whether to go become a physicist or musician and so that my parents made the decision for me and once that's sort of go into physics I sort of get drawn to very fundamental thing. I really want to understand, physics at the fundamental scale. And I would also say, when I so 我在台大念大学 and when I was applied to grad school, 在申请研究所的时候 I was also struggling, right? Because I had the feeling that, doing particle theory, it doesn't really have a very close impact, direct impacts on human being, right? So I actually was struggling and considering maybe going into biophysics because that's something that can be related to medicine and that would have more direct impact. But in the end, I stayed in theoretical particle physics just because, you really get to understand phenomena at the most fundamental scale level. And the math is very beautiful, right? It's a single equation you can fit on your t-shirt and that predicts all the interactions, all the experimental signatures you should observe, and that's just very robust. And of course, now thinking back, I mentor students, I work with students, and that's sort of a way that I impact the human being. So I think from that aspect, I think I choose the right career and happy with it.
那个钱教授只提了前半部，就是到从高雄到台中到台北。那后来到美国之后呢，其实我刚刚也没有介绍的是，陈教授是在 Colorado 拿到博士学位，是在美国的中间。那后来又到长岛，是在美国的左边，还有 Chicago 是在美国的北边，就是有2个那个 lab 当 postdoc。那现在在加州是在西边，又偏南边的地方。那在每一个地方这样子，这是一个什么样的契机吗？还是你的想要看看不同的世界的地方这样子的一个？
所以 Okay, good question. 基本上
is it a tendency or is it just happen?
It just happened. 所以那时候就是申请博士后研究员，然后两个国家实验室都是I mean they have very good program, excellent research opportunities there. 所以在 Brookhaven 国家实验室在长岛，基本上它是我开始跟 Neutrino experimentalists 有很多的interaction. So I think that's a very, very important part. Even though I do theory, but I do participate and have very close interactions, discussions with the experimentalists. 然后从长岛之后搬到费米实验室，在里面待了1年。然后费米实验室那时候是全世界有最高能量的加速器 ，right? Before CERN, before the LHC, it was Tetrahedron at Fermilab. 所以在里面待了1年，然后再搬到加州来。So it's yes, I think it's sort of have the opportunities there. These are places which are pretty exciting because the experiments out there. 然后你就是在you are working at a place where the discoveries are being made. So I really enjoyed the time at those 2 national labs.
Thank you. 我想我们还有一位听众，那他有一个很专业的问题，他问到说 electrons and positrons can generate or each other in a vacuum, especially when the universe was first born in a small and hot environment. How vacuum happen?
Right. So this we don't know, right? So this is the ultimate question. What is the origin of the cosmological constant? It's a very tiny number. It's non-zero, and how do we explain that? And so far, there's no satisfactory answer yet to that question. Right. So when we say vacuum, it's not really vacuum, but there are quantum processes going on.
Okay, so
I don't have a good answer for that.
That means our young audience should be encouraged to dive into this field and research into it together and show us how it goes. Okay. I believe there are a lot more to talk about, but our time is up. And I hope we can soon have another talk inviting Professor Chen again. And if Professor Chen comes back to Taiwan, especially Pingtung, which is my hometown too, please let us know. I can show you around your childhood places. Make sure, let us know. Before we meet again, I believe everybody can contact Professor Chen for further questions in private by emails or any other means. And thank you again, Professor Chen, for sharing with us today.